I'm Brandon Seymour, and this is AI in 5, where I break down complex AI infrastructure topics in 5 minutes or less. Let me ask you a question. When most people think about AI infrastructure, what is the first thing they think about? Usually it's the GPU. How many do we need? Which model? How much memory? How fast is it? And those are fair questions, but they also are where a lot of organizations get distracted. Because you can buy the best GPU in the world and still end up with an AI platform that is slow, expensive, unreliable, or unable to scale. Why? Because the GPU can't operate by itself. It needs power, it needs cooling, it needs memory, storage, networking, software, security, and access to the right data. And every one of those pieces need to work together before the business gets anything useful out of it. So here's the idea I want to unpack over the next few minutes. The GPU is not the AI factory. It is one machine on the factory floor. The real AI factory is the complete system that turns electricity and data into enterprise outcomes. So let's make this real. Imagine a retail business where someone asks the AI system a simple question. Which store is most likely to run out of a popular product this week? What the user sees is one question and one answer. But behind the answer, the entire AI factory activates. Now, the magic begins. The platform first confirms who is asking and what information they are allowed to see. Then it finds the right business data, retrieves the relevant context, sends the context to the model, and validates the response before anything comes back to the user. And this happens at the speed of light. And underneath the workflow, even more is happening. The request is being tokenized, the model moves through prefill and decode, memory is being used, data is moving across the network, the system is drawing power, generating heat, being cooled, and scheduled alongside other workloads. So when the user sees store 214 is at high risk, rebalance inventory today, well, that answer is only visible output. The AI factory is everything required to make that answer accurate, secure, timely, and useful. Now let's look a little deeper at what the model is doing, because inference actually happens in two distinct phases. The first is prefill. Prefill is where the model reads the full question and all the information that comes with it. In this example, it starts with processing our question, which store is most likely to run out of a popular product this week? It processes the information in parallel and builds the working memory it will use to generate the response. This phase is more compute intensive, and it has a major impact on time to first token. In other words, how long you wait before the answer begins. Then we move into decode. Decode is where the model builds the answer one token at a time. For example, it generates store 214 is at high risk, rebalance inventory today, piece by piece until the full response is complete. At this point, memory bandwidth becomes especially important because the system is repeatedly pulling the model weights and the KV cache as it creates the new token. This phase affects how fast the rest of the answer appears. And this is why one benchmark never tells the whole story. A system can be strong at prefill and weaker at decode, or behave differently once you add longer prompts and more concurrent users. Now, we get to one of the most important physical realities of AI infrastructure, and one of the hottest topics in the industry today. Electricity becomes heat. These days, a high-density AI rack can draw around 120 kilowatts of power. To put that into perspective, that is roughly the same as running 80 typical 1500-watt space heaters continuously, and nearly all of that energy eventually has to be removed as heat. This is why power and cooling have to be designed together. Power determines what you can install. Cooling determines whether you can actually run it. At lower rack densities, air cooling may be enough, but as AI systems continue to become denser, liquid cooling moves from being optional to becoming part of the core architecture. That means that the conversation is no longer just about servers and GPUs. We have to think about things like coolant distribution units, facility water loops, flow rates, temperature, redundancy, and heat rejection. So, before the organization buys the hardware, it needs to answer a much more basic question. Can the facility support the power and remove the heat? Once we move beyond a single GPU, everything changes. Many enterprise AI servers use multiple GPUs, often 4 or 8 in one system. The GPUs now have to work together as one system. At this point, the network becomes part of the overall platform. The high-speed network lets the GPUs share data, stay in step, and keep working instead of waiting on each other. But the network is only half of the story. The software layer, including platforms like Kubernetes, Run AI, and ClearML, control how efficiently the AI systems run. It decides what work happens first, groups similar requests together, reuses information when possible, and sends each request to the right model or resource. It also helps us see where the system is slowing down or wasting capacity. So at scale, performance is not just about the GPU. It depends on how well the network and software help all the GPUs work together. The goal is not simply to keep the GPU busy. The goal is to produce useful business results at a lower cost. So when we step back and look at the full picture, this is what the AI factory really is. It starts with electrons. Those electrons power the facility, the compute, the memory, and the network. The platform then brings in enterprise data, applies the software layer, and turns all of that infrastructure into an outcome the business can actually use. And that is the point I want to leave you with. The GPU is one machine on the factory floor. It is important, but it is only one part of the complete system. More GPUs will not help if the rest of the system cannot keep up. The limitations could be powerful, like power, cooling, networking, data, or software. So instead of asking, how many GPUs do we need? Ask, what complete systems do we need to create a useful business outcome? I'm Brandon Seymour, and this has been AI in 5. If this was helpful, please like the video and subscribe to the channel for more practical AI infrastructure conversations. And if you want to read more about AI, enterprise infrastructure, and the systems behind it, visit me at virtualizationvelocity.com.